we have Arjen Lentz here, who is going to be talking to us about his OpenActa project, Haystack, and how different it is from other log stores, and further in-depth information that's going to be of great value to us. Everybody, Arjen.
Good morning, and thank you for coming. That's a decent crowd. I wasn't sure what to expect. You never know. So thank you. So yes, I'll be talking about Haystack, which seemed like an appropriate name for, you know, when you're collecting logs and then you actually need to find stuff, you know, needles. So there you go. As it turns out, there's lots of things called Haystack online. So if you just Google it, dreadful things happen, but it can be things can be found. So I'll first explain what the basics are of that, then explain what makes it special, and go into some other bits around that. And right at the end, I'll explain why we might not actually need it at all, but it might still come in useful. That's up to you guys and you know, other people, depending on the questions I get, depending on the support I get, and all that. Okay, first of all, what is Haystack? Why am I reinventing, you know, event log storage and so on? By the way, anybody can get my slides. I've got a USB stick with me. You can just copy them or ask me, send me an email, and you will just get a copy of the slides. Not a problem. So why am I reinventing this issue? Cost, licensing, all that kind of stuff is hindering a lot of log stores. Even the ones that are supposedly freely-ish available, you can't stick in more than 5 gigs of data, or you can't log more than 5 gigs of data a day, or, you know, there's all kinds of little encumbrances, so we say, so restrictive licenses, and I think that's a problem, and I'll explain why that's a problem. Costly. Well, yeah, you get, I would call, taxed for the exact thing you need, which is ingesting data. I know of some, I can't name them unfortunately, but I know of some very, very critical government departments who reduce their event log intake because they can't afford the licensing to actually store it all. It's like, I understand where you are, but it's really, really not good. And if they can't afford it, can a small business afford it? And that's also a really big problem. It's from really big to really small. That's what we're talking about there. And yeah, so amount ingested, the total amount stored, all those things are taxed by different companies. I realize that companies want to make money. That's great. But my primary concern is security. That's my business since about 7 years, since I moved away from talking about MySQL and MariaDB databases most of the time. You may remember me from that time too. Yeah, so logging is really, really important. We must know what is going on in order to prevent problems potentially, and at very least catch issues the moment they arise rather than a long time later. The average time of finding an issue within an environment, so let's say a company, used to be about 18 months. You can just imagine the amount of damage people can do in 18 months. It is not funny. You know, they can get in and grab all kinds of data, get themselves, you know, pivot and get themselves into other systems, just monitor email communications or other new files, modified files. It is not good at all. Now, the time from gaining entry to actually being able to do stuff maliciously, so elevated privileges, pivoting and accessing more systems, getting onto Active Directory if it's misconfigured or gets an update and therefore misconfigured, you know, all those reasons. That time has reduced in recent years. So if the detection time stays at 18 months, we're at the wrong end of that particular battle. The baddies don't care, is what I always tell my clients. They really don't. The fact that the company says, yeah, but we can't afford this, or that is not our priority, the baddies don't care. They will do what they will do for their own reasoning. They don't wait until you have time to put something good in place for covering your security. So the licensing of Haystack is AGPL version 3. Reason for that is I like GPL a little bit more than BSD. I know other people like BSD more than GPL, and we can have the conversation over a glass of ginger beer from my end and beer from your end. That's all good. AGPL from my end, because I don't think it is cool that a software as a service company, let's call them Amazon, for example, just an example, would make improvements to the software, but then not actually give access to the users of that software to the source code. The ability to actually look at the source code, improve it further, and so on. AGPL actually gives that guarantee in addition to the regular GPL licensing arrangements, and I think that's pretty cool. And it just happens to be called the Avera GPL for historical reasons, but it's actually a pretty slick license. It works. So that's the intent. The improvements, modifications, and bug fixes should be available for everybody. Makes sense. So Haystack has a very different architecture, and I'll run you through what it contains. Here you go. It's a bit slow. It's funny. First of all, and this is where my database background comes in. One database is not better than another. You know, there's always the conversation still to today. What is better, MySQL or Postgres? No, wrong question. What are you trying to do? What is your system actually architected for already? Because if your system is architected for a particular type of database or storage system, like an object store, for instance, or a key value store, then it's probably architected entirely for that, it's optimized for that, and it wouldn't do particularly well in terms of performance and being able to find things and store things quickly and memory usage and all that for using anything else that you may be able to attach to it or hack in. So there's no single best way of doing things, but depending on what you're trying to do, there may be a better way of doing things for that particular purpose. So that's where Haystack comes in for event logging. A data lake is, I'm just going for unstructured to, from unstructured to really, really structured. A data lake is just a pile of data you tossed in a lake and you hope that you can find it again. It's a very interesting mechanism, and we can get away with that because we have vast amounts of storage. We can waste RAM and CPU time on actually being able to find stuff. It's really lovely when you run in the cloud and actually have some spare money to manage all that. I'm not a particular fan of data lakes. I think we can do better. But that's just, again, it's something to discuss over a beer. Key value stores, they're not particularly structured, but they're an interesting mechanism, of course. Tools like Redis are absolutely awesome for what they do. And there are many other key value stores that do similar things, of course. Redis has now been, is being competed with by others, I forget the names, because of licensing hassles and so on, and cool. So then there's things with predefined structures that can often create hassles because needs change over time. the things you want to store may change. You know, you may start using extra systems in your environment. In the case of event logging, you might acquire new switches, new routers, entire new brands of tools. You know, you may be mostly a Windows environment, but you now start acquiring Macs as well, Linux boxes, whatever. It can be very diverse. You might move from one cloud to another and therefore get an entire differently formatted set of data and different types of data. So managing those changes, if the, let's call it the schema, is predefined, is awkward. It can often be managed, but then accessing the older data is awkward. So, you know, what do you do with it? If you predefine that kind of stuff in a key value store, you very commonly get a lossy ingest. So if the key value store says, okay, I can deal with these keys, but not other keys, then if you toss certain keys in, it says, oh, toss, which is effective, but again, you're losing data. I don't like losing data. I think it's valid to filter, but not for these technological reasons. It must be, or financial reasons. I think it should be, or business reason even. I think it should be for an architectural reason, you know. I really don't need that data, I'm damn sure, or I know that I'm getting this particular type of log entry. I just want to know how many of those per hour I get, and then you can rate limit them. You know, that kind of stuff happens, and that is perfectly doable. And finally, of course, a relational database is very specific in structure. We'll get back to that. Okay, so a brief sideline, because it is actually relevant. What's the difference between a relational database and a spreadsheet? You may remember these from my database talks. They are not the same. They look really similar in some cases, but they're really not the same. At the very basic level, the top two lines, you know, each row has the same number of columns. You don't often think about that, but they do. And each particular column is always in the same position in a row. It doesn't suddenly move around. And the column is definitely there because of rule number one. And then there are a couple of other things, but those are the main things. And by the way, a relational database has nothing to do with the relationships between tables. A relational means table means set. And a set comes from set theory. And for that you have to think about Venn diagrams. You've had them in either primary school or high school. Most of us have played with them, and you didn't know it at the time, but you were playing with relational databases. So there. So a spreadsheet is not a relational database because it doesn't adhere to the above rules. You can do anything you bloody like. I love spreadsheets. They're one of the best inventions ever, but they are not a database. And that is where people go dreadfully wrong. So each cell, and they're cells, not columns, to think about them properly, can be a distinct data type. So if you think about a particular column vertically, then, you know, column A, one cell can be a string, and the next one below that can be an integer. And if you add those two up, you're going to get funny effects, probably errors. In a relational database, you can't do that. Except in SQLite, because it doesn't care, but it has protectional measures to deal with that. You know, there's a way to work around that. Actually, MySQL used to also have tricks to work with that kind of stuff. So, yeah, a cell doesn't even have to have a value. It may actually be a black hole. You can't see them, but they may not contain anything. And that's why we call them, the people who might implement them, they might call them sparse matrices. So if you store a spreadsheet, not all the cells are stored, only cells that contain a value are stored, and that makes them much more efficient in storage. You can kind of, well, it's not quite compressing. All the data, well, all the non-data doesn't actually exist, which is a lovely thing. So the reason I'm telling you this is because to create a functional mix of a spreadsheet and a relational database. It's a bit quirky, but bear with me. Because it can be done. And I didn't even come up with it. I'll give due credit near the end with photo and everything. So, what am I trying to get to with the OpenActa project? And again, it may already be partially done, and in that case, I'm happy to yield and just move on and help that other project. But you know, there might still be things that need to be discussed. So once you have an event log store, you need to start being able to search that, and you need to be able to take actions based on those searches. And for that, you might use a SIEM. So it deals with system information and event management in particular. What SIEMs start to do, and event detection and response systems, and things beyond that, and by the way, all those names, they're kind of like SIEMs plus the latest marketing hype. An EDR and XDR is nothing more than the latest marketing hype on top of what a SIEM already does. So don't worry about those bits of terminology too much. Typically what they need to do is run a heck of a lot of queries at different intervals. So some of them you may want to run every 5 minutes, others you may need to run every 2 weeks, and lots of time in between, because you want to see what's going on in your environment. You want to see whether any user has had at least 3 failed login attempts over the last couple of hours from outside the country. Just giving you an example, because that can indicate that someone is trying to brute force access onto your environment, right? There are hundreds and hundreds of queries like that, and they're useful. And there are online repositories for that kind of stuff. I'll have reference to those later, and they're on GitHub, and you're just free to use them, you're free to contribute to them, and that's awesome. So that's one thing I don't have to worry about. It's already done. People way smarter than I am have already dealt with that. But the point is that we need to be able to run lots and lots and lots of queries. It is not just about the person in the SOC sitting in front of their screen, running a particular query when they get a question or see an alert. Those alerts on their own are generated by lots and lots of queries, and they bring up the alert that then needs to be investigated. That's how that should work when things are properly set up. So we want to seriously collect as much data as possible about what's going on in the environment. And there's really no limit to what you can collect. You might need to be selective in some ways, but again, not for quirky reasons like licensing, money, and so on. You definitely don't know beforehand what you're going to want to search. That's what I mentioned earlier, and your needs will change over time. What is true though with event logs, and untrue for regular relational databases, is, or how they're used, is that with event logs you typically want to search on recent data. You want to search in stuff that's from the last day or the last couple of weeks, you know, that kind of stuff. You want to know what happens in the last couple of weeks so you can keep track of your patterns. you know, the login profile of each individual user, what time in the morning do they log in, what time in the afternoon do they log out, that kind of stuff. And you can keep a window of knowledge on that. And other than that, you really only care about what's going on within the last day, just to see if there's funny stuff going on, as I gave you the example last time. You must be able to access older data, though, for forensics. So let's say you find something nasty, you want to know when the real nasty started, way back. You need to do a root cause analysis, essentially, but on your way there, you're going to be tracking a lot more data, because before they were doing the particular nasty that you spotted, they were probably doing something else to get there, and in the end they got in, or at the start they got in, and you want to find that point, because that is the critical point that was really insecure, the entry point, you know, the attack vector. And then, of course, we have something called the chain of custody. So for insurance purposes and potential court purposes, there needs to be the chain of custody, which means that your logs may become evidence. They're part of the discovery process of an investigation, and it means that you might need to prove that the logs you have on disk or in S3 or, you know, wherever you keep them are actually the original depiction of what happened. No one could have even tampered with them, and so they should be encrypted with the encryption key somewhere else, and they should be signed. Right? Make sense? And signed doesn't necessarily mean a cryptographic signature. It just means that if you're going to encrypt them anyway, no one can muck around with them directly, but then you take a SHA-256 or a SHA-512, you put that SHA signature somewhere else, then if someone messes with the document, recreating an exact SHA hash is rather difficult, as we know. That's a cryptographic impossibility at the moment, so you're good. You don't have to do a cryptographic signature per se. You can do a SHA, which is the quick way of doing that. So you don't have to worry about cryptographic signatures that are quantum secure in that sense, other than the hash method for it. So that's the chain of custody. And that is the one thing typically that other log data stores at the moment don't do. And that includes big brands that you can use as a service online. They will give you the service for logging all your stuff and maintaining that and so on, but that chain of custody is really, really a problem. And governments are becoming more picky about that, and insurance companies are becoming more picky about that. And, you know, once lawyers get involved, it gets really, really complicated. And you want to be seen to be doing the right thing. Okay, so once you've stored all this stuff, how are you going to find stuff? Well, there's a number of ways of doing so, and again, we're playing with databases essentially. Hash lookups. You have a number, you use an algorithm on it, which puts you in a certain area of your total storage space. Should there be nothing there, then you can put your, you know, in case of a search, then you know if there's nothing there, there's no find, you know, there's nothing found. For an insert, if there's nothing there, you can insert it there. Should there be something there, but it's not what you're looking for, then you have a rule on hopping along until you find an empty spot. Or you've looped around. So there's some ways of doing that. In any case, hashes are really, really quick because they're in memory, but they're not efficient to work with on disk. you need to convert them in some on-disk format, and that conversion process, both out and in, is a bit messy. So typically a hash index is not stored on disk. A binary search. We all know, or at least should still know, what a binary search is, because we used to use them. Back when you open a telephone book or a dictionary, you know, you need to look up something that's near the L. Where do you open the dictionary? Anybody? Somewhere in the middle. So if I'm looking for a W, where do I open it? Towards the end. Excellent. Okay. So a computer is a bit more stupid. It always starts in the middle. But you know, it'll get to the W quick enough. You know, it's a bit quicker at getting there, but it's a bit more stupid about starting. So that's a binary search. But they are very, very useful, and I'm going to be using them in Haystack. Basic trees. Trees are a little bit different because you have a root, and then if which again starts essentially in the middle, which by the way isn't L, it's either M or N, if you're not looking at distribution. Like in English, there will be lots of E's, S's, and you know, funny other things, but the middle of the alphabet, M is the 13th letter. So, anyway, a basic tree. You start in the middle, and then if you need to be lower than that, you go left. If you need to be higher than that, you go right. And you keep doing that until you find what you need to find, or you find that there's nothing there. So that's a tree. A B tree is kind of the same thing, but in blocks. Why? Because originally we had disks that ran in sectors, and then the sectors ran on cylinders on those old spinning disks, and it was way more efficient to, well, for starters, you couldn't read just a couple of bytes, you had to get the entire sector or a larger chunk, and it was actually quite efficient to read an entire cylinder because you were there anyway. It's funny, the slowest point of the old physical spinning disks was the head movement, which was counted in milliseconds. It used to be like 20 milliseconds, and it went down to 2 or 3, I think. And after that, we gave up. We just developed SSDs. And now NVMe. And the world is wonderful, right? The world has improved. So B trees store an index, you know, essentially key values, roughly, you know, column and the value, or an entire row for a relational database, in the form of there's one set of data, then the next set of data, next set of data, next set of data, next set of data. But each of those entries has a pointer to the left. So your tree becomes very wide. Does that make sense? So you have thick branches, and each of those branches has a number of little branches already. And all the way at the end of that block, there's one pointer to the right. Okay? So it's more complicated to draw. Computers don't care. The cool thing about both a regular tree and a B tree is that it's way easier to insert stuff, because you have to rebalance the tree, because you don't want that path of the tree to be 10 times as long as that path. So in a binary tree, you just want to reattach it. Instead of being here, you want to reattach the branch to be there. So you just grab it, put it there, and all is well. With B trees, you can rebalance them as well. So they're essentially, and they're called self-balancing B trees are B plus trees. You can look them up on Wikipedia. The algorithms are there. It's entirely straightforward. I did that, I don't know, 35 years ago. It's not new. So that's why those things work that way. So you use a tree to make inserts more convenient, more quicker. A binary search is difficult to do an insert on, because how do you insert a page in your dictionary? Yeah, you can do that a few times, and after that it gets really bulky and annoying, you know, all those sticky notes. And if you think about it in the computer, you could use pointers and then shuffle the array, or you could shuffle all the data and then insert it. But you can imagine it becomes more inefficient the more data you have. So it is not the best way of going about it. So keep that in mind, I'll get back to it. Then there are Bloom filters. What you did before with my question about the W is a Bloom filter. You take a shortcut. So a Bloom filter is a programmatic trick that first of all indicates whether data exists under the W, because if that doesn't, you don't need to look there. And secondly, if the W does exist, where to start. So it takes a shortcut into the binary search, for instance. So that's really cool. At the moment, Haystack doesn't use them because it doesn't care. It doesn't have to care because it's fast enough. Let's continue. All right, that's Haystack. And that's all there's to it, end of my talk. Now, so it's a key value store, but with extra fields, okay? So you have a key, you have a value, we knew that. There's also either an additional key that you provide, or that gets generated on insert, you know, it depends on the implementation. I mean, in my reference prototype implementation, I think it's microseconds, timestamp that is always, you know, see it as a primary key or whatever, but it's always there. It doesn't have to be unique. It's always there. So that gets added, and it is the first of that set of key values, and I'll explain why it's the first. And then there's also a next pointer. So there's a first pointer and a next pointer. All of the key value entries, except the first, point to the first. So they can find the start of their row. Does that make sense? Secondly, they point to the next field. So find any of the key values that you were looking for, any of the keys that you were looking for, and the little chunk of data in memory where you found it, you can hop to the first entry and get all the data that belongs with it. So imagine, for instance, an event log from either Windows or syslog, has lots of little bits of data, lots of fields. You want all of them, yeah, to be able to actually get enough detail on it and zoom in on that and do proper analysis on it. And possibly even filter it further to get to exactly what you need to know. That can be quite important. So you can get to the first bit and then zap through it. And the way you find the other bits, of course, you search for them again using the same index. Everything exists in the same index, they just point to each other. As I mentioned, a bit quirky, but it just works. There's no reason why it shouldn't. It just hasn't been done before. And the final field in that chain points to null, which means nowhere. Yeah, so end of chain. So there you go, easy. The keys themselves are not stored directly because that would be a very wasteful exercise. So a key, well, it's not mentioned here, but at the moment Haystack is a JSON store, so it's a string. It's a piece of string, and it's a flattened JSON store. So, yeah, we don't want to store every time a particular key comes up. We toss it in a hash table, and the ID, which is the location in the hash table, that is what we use for the key. Easy, right? So if you want to find a particular key, you look it up in the hash table, and then you find it in your using your binary search. Once you're dealing with the row itself in that environment, you already have the number, so you don't need to use the hash table anymore. You can just go directly into your binary search, and you get there very, very quickly. Okay. What else? Yeah, so timestamp is always in UTC. I'll just keep mentioning that until people actually start doing it. It has nothing to do with the design of the system, but I see so many logging environments where people don't use UTC. You know, they use Sydney time. Well, that's fantastic, but only for part of the year. And then they start deploying in multiple data centers across multiple continents, and it all goes to blah with various expletives from asterisks added. So please just stick everything in GMT, problem solved, or UTC, problem solved. Convert them before you get them anywhere close to your logging store, and all will be well. Time zones are something, and very expensive tools like Splunk actually understand this. Your user profile has a time zone. They understand it. So they do get it right, but that doesn't mean that the people who put data in get it right. It's a user interface thing. It's a layer 7 problem, nothing below that. Okay, so other basics. And I'll run through that very quickly because I've already mentioned stuff. While we're adding data, it won't actually be accessible. So you can't search it at that precise moment because it's not yet sorted, so there's no binary search possible. So the latest data, and that will probably only be like the last half minute or whatever, depending on how busy your system is, will not be sorted. At configured intervals, it will be sorted, and at that point we need to go to a new chunk that is not sorted. Make sense? That is actually exactly the same thing that Spanner uses, or what you may remember as Bigtable, what Google had, and they didn't invent it, they grabbed it out of an academic paper from before, and there's now other stores that do similar things. So, when there's a sufficient amount of data, those chunks collected, rewrite it to disk, and first of all we deduplicate identical values, which will often be adjacent, because they might have the same, they're very likely to have the same key, and things that have the same key very often have the same value. So we just, instead of having that value, we actually point to the previous value. We just say it's repeated. And that is permanent, because once we write it to disk, even if we read it back, it still keeps that in mind. So it's just, again, a little shortcut to save some memory and some disk space. Now, before we write it to disk, we compress it, LZ4, which is the same compression system that the kernel uses at the moment. It's bloody good. It's the same as bzip2-9, also known as very good. And it's 3-to-1 or better. I think the or better applies here because it's a JSON store, mostly text, so better. Yeah, we're not compressing a binary, we're compressing text. SHA-256 GCM, so that's good encryption, Yeah, that's quantum secure for the foreseeable future. EAED, if you're not familiar with that, means that it's, I'll give you the quick version of it. When you decrypt a block, the decryptor can actually identify whether it's decrypted a valid block or not. So should the data, the encrypted data, have been compromised, that could be maliciously or through some data corruption, when you decrypt it, out comes garbage. Normally you wouldn't know when it's garbage. With EAED, you do know when it's garbage. So you know whether it's valid data or not. So I don't have to put in any effort with signatures and other blah to help with that. I put a CRC32 in anyway. Maybe I'll remove it, thinking about it. Doesn't really matter, they're cheap. And then the SHA-512, which is kept separately. That's the signature. Why 512 instead of a 256? Because they're essentially the same algorithm, and why not? They are two very cheap. An index of all files is kept, again, separately, and for a file, you would keep the start and the end of that particular thing, of that particular file, and then that means that if you want to go back 2 weeks, you know exactly which files you need to look at. It is that easy. And files are immutable after they've originally been written, so, you know, makes life easy, and then you start a new one. Okay, how do you retrieve? I've already mentioned most of this, so I'll go over it really, really quickly. It could be stored in S3. You know, once you run out of local disk space, or you don't want to care about them anymore. Recent files you want to keep locally because you don't want to have to keep paying for S3 storage and retrieval costs. But I'm not saying you should use S3, I mean S3 equivalent. You know, there's lots of things that talk S3 API without being S3. And the search process is, as I described, you find something that's within your date range. If you have something without a date range, you're going to have a very inefficient search. That's not a good idea. It also makes no sense at all. You need to know whether you are looking for something within the last hour, the last 2 weeks, or the last year. If you don't, you need to sit down at the table, talk with some colleagues, and figure it out what you're actually looking for. That's really important. It just makes no sense in event logging space. Searches with this kind of architecture become inherently scalable and can be distributed, because it really doesn't matter where you read that particular file. You can put it in 2 different places, and you can even search. You can do part of the search here, part of the search there, combine those searches, the result sets, and then give it to the client. You can have a proxy parse that information and finish it all up. All data sources should definitely be in a single data store, because otherwise you just make a mess of things, and that is something else that other data stores have trouble with. And I think I'll leave it there. So that's all the current information, and that's the guy who actually came up with the idea. That's my friend Anthony. He used to work at MySQL as well, together with me, and he came up with the idea of the interlinked records, and I think it's pretty cool. So I now need to fess up on why this might be completely unnecessary. I understand that the component of Grafana called Loki actually does a pretty good event logging mechanism, both in search as well as in scalability and so on. So it might actually do most of the bits, except it doesn't deal with the immutability, but in particularly the, you know, like the cryptography and the signatures and that kind of stuff. So the chain of custody is not dealt with, which is important. I'm not sure we're quite there. I don't know. But I'm just saying they've done awesome work already, so this may just have been a fun way for me to learn Go, which was actually the reason I was doing it. So there you go. Okie dokie, that's it. Thank you very much.
All right, had to change microphones. I had a 2-line education on radio signals and crossover and feedback. Arjen, thank you so much. That was really, really interesting. And I'd like you to give you this lovely little item.
Awesome.
Not sure what we call it, but display it with pride as being one of our speakers this year.
I will. I've been wanting to look at that in close up.
Now you
Thank you.
Thank you.